Welcome to No Calc, the series that explains how math got done before the 20th century. Today we will be going over square roots. So we'll be going over three different methods in order to figure out how we can do it. The first one is kind of a guess and check method, which would probably be the first one that would come to mind to most people. Then we'll show a fairly simple but really fast method for calculating square roots using averages. I'm sure a few of you are aware of this. If you find this method to be something you already know, stick around because we'll go deep into the theory behind it and show how some of our error bounds can even help us get a little bit farther without too much more calculation. So let's get started. So suppose we wanted to go figure out what the heck is going on with the square root of 7. Now, the first thing that you'd probably do is know that 2 squared is equal to 4 and 3 squared is equal to 9. So our square root must be between 2 and 3. Kind of a guess and check method. Now what we could do to go farther is we could check decimal places. So we could say square root of 7 is probably a bit past half. So if we wanted, we could take 2.5 squared. And if we calculate that, we'll end up getting 6.25. So that'll be less than it. We bump up to 2.6 squared. Calculating this will give us 6.76, getting us a little closer. So we bump it up a second time to get 2.7 squared, which we'll calculate to be 7.29. So if we do this method, we will end up showing that 2.6 is less than the square root of 7 is less than 2.7. Now, this is a good starting method. We can be able to calculate usually to one decimal place pretty reliably for these numbers, but it's not the fastest. So, how can we improve this method? Well, one thing that is helpful is the fact that square root of 7 times the square root of 7 is equal to 7. So instead of trying to deal with the square root itself, what if we take two numbers, a and b, that also multiply to 7? Now, how do we find such a number? Well, we can just guess and check. So, if we take a square root nearby 7, so maybe 3, what do we multiply to get 7? We multiply by 7/3. And this will give us 7. Now 7/3 is less than 7. 3 is bigger than 7. One might think to just haphazardly take the average of the two. So we take 7/3 and 3. This is equal to 9/3. And our average would be 8/3. Which is about equal to 2.67. Now, what actually ends up happening is if we look at this number 2.67, this is already between 2.6 and 2.7, and we didn't have to square any two-digit numbers in order to do this. And it turns out that this method, surprisingly, ends up being very quick and very fast. In addition, we automatically get error bounds on our square root. We know that it is between 7/3 and 3. Why? Because they multiply together to give us 7. This one's smaller and this one's bigger, so we must have the square root inside here. Now, what if we wanted to get a better approximation than 8/3? Well, we have a better guess, so we could just do it a second time. So, we want 8/3 times some number to equal 7. So what we can do is take 8/3, take the reciprocal of it, and multiply it by 7. This is what happens when we solve for this number b. We'll get this is equal to b. So we get 21/8. Now this one will happen to be less than 8/3. And so let's try doing the same method again and haphazardly take the average of the two. Now this one's a bit trickier to take the average of, 21/8 plus 8/3 over 2. That's how we take an average. One method I like for doing this is computing fractions by cross multiplication, almost. So if we have two fractions, a over b plus c over d, we can compute this product by multiplying a by d to get ad over bd, multiplying c by b to get bc over bd, and then we add them together and get ad plus bc over bd. So essentially, we multiply these numbers together, add the multiple of these numbers together, and then divide by the product. So, for our example, 21/8 plus 8/3, we would get 21 times 3 is 63, plus 8 times 8 is 64, over the product, 24, and this is 127 over 24. Now, since we're taking an average, we have to divide this by 2, which means our guess is going to end up being 127 divided by 48. And we're down to one long division. And we get that our answer is about, our approximation is about 2.6458. Now, how close is this? Well, based off of our initial fractions, we had 8/3 and 21/8. So we know our number must be between 2.67, being 8/3, and 2.625, which means we're off by at most, our error is off by at most 0.03-ish. Now what's surprising is how quickly these answers actually get to the right answer. Now, we may have seen that our error was less than 0.03, but in fact our error is much less than that. It is probably within 3 digits of the correct answer. Now, why is this method such a good method? Well, it has to do with the theory behind what's going on. And in order to go over the theory, we got to go over different types of averages or means. Now, our first standard type of average, if we take two numbers a and b, we can add them up and divide by 2. This is known as the arithmetic mean because we're doing arithmetic and just taking an average. But we have different types of averages. For instance, what if instead we consider a rectangle with sides a and b, its area is AB. So we could consider an average to be the square that has that side length, which would end up being the square root of AB. This gives us a second type of average, the geometric mean. Root AB. Now, what is fascinating about the geometric mean is there's a famous inequality called the geometric mean, arithmetic mean. Usually, actually, it's said backwards. The arithmetic mean, geometric mean, or AMGM inequality. And that says that this inequality is strictly less than the arithmetic mean, as long as your numbers are not negative. Now this should be a bit surprising, because what we're doing is we have two numbers AB that multiply to give us n. So the square root of AB is equal to the square root of n. This is what we're looking for. We are approximating it by using this side, a plus b over 2. And that guess that we're making is always going to be strictly bigger than the actual answer. For instance, if we take two numbers, let's say 4 and 16, their geometric mean is 4 times 16, the square root of that, which is equal to 8. But if we take their normal average, we would get 4 plus 16 over 2, which is equal to 10, is always bigger. Now, why is this the case? Well, suppose we have a plus b over 2, and we're considering root ab. Now, if we subtract the 2, we'll end up, we want to show that this is bigger than 0, because that would show that this number is bigger than this one. Now, it may not seem like it at first, but if we write it as this form, this ends up being a difference of squares from the square roots. We actually get root a minus root b squared over 2. Which is fascinating because a square is always greater than or equal to 0, and dividing by 2 doesn't change that, so our number is always greater than or equal to 0. But we can do a bit more than that. We found that our difference, which we'll call epsilon for the error, is equal to root a minus root b squared over 2. Now, I don't like these square roots because it's kind of difficult. We don't actually know what the square root of our numbers, like 8/3 and 21/8 were. Instead, let's multiply by the conjugate, or by the same expression but with a positive instead of a negative. If we multiply that to the top and bottom, we'll get this over root a plus root b squared, which is equal to, using difference of squares, a minus b, a plus b, will give us the square of that minus the square of this. So we'll get a minus b squared over 2 times the square root of a plus b, or the square root of a plus the square root of b squared. Now, this might not look simpler, but it is more useful. For instance, let's say we want to find something that is smaller. Now, we've said that this is equal to epsilon. So what can we do to make epsilon smaller? We can make this denominator bigger. So first off, let's just say that a is the bigger one of the two. Then, if we replace both of these by a, this will actually end up being smaller. Now, when we do that, we actually end up getting a minus b squared over 2 times 2 root a squared, which is 8a. On the other side, we can do the same thing, and it will be bigger, or it'll be smaller than this over 8b, which gives us some excellent bounds on how far off we are. So not only do we know that our answer will be off by at most this amount, but we can actually bound it between two other numbers. Let's see some applications of this. First off, let's suppose that we're trying to take the square root of a number n, and we've got it between some numbers k and k plus 1. Now, we can choose one of these that will allow us to be close enough to n so that our other guess, when we divide it, will be also in this range. We can always do this because n will be somewhere either above or below k times k plus 1. We can either pick it between k squared and k times k plus 1, or k times k plus 1 and k plus 1 squared. So, if we take it here and make our guess k, our other guess will be less than k plus 1. If instead we make our guess k plus 1, because n is in here, then our other guess will have to be bigger than k. No matter what we do, for our first guess, we'll have a minus b, our error, is less than or equal to a minus b squared over 8b from before. This is going to be less than or equal to the difference between our guesses, which is going to be less than 1, squared, which is 1, over 8 times b. b being the smaller one, it'll always be smaller than k. So after guessing off of one instance, our error is automatically going to be within 1 over 8k, which is really tight, actually. In our computation of the square root of 7, the square root of 7 is bigger than 2, and so our error is going to be less than 1/16. Now, what other things can we say about this? Suppose, if the number we're taking the square root of is bigger than 1, then we automatically know that k is bigger than 1, and our error will be less than 1/8. If n is bigger than 25, then k will be bigger than 5, so our error, which is less than 1 over 8k, will be less than 1/40th, or 0.025, which means that our first guess can be ridiculously close, within almost 2 digits of our answer. Now, our first iteration can also be done practically in our heads. For instance, take the square root of 17. Now, a good guess for square root of 17 would be 4, and then 4 times 17 over 4, which is 4 1/4, will give us 17. We take the average again, being 4 1/8, or 33/8, or 4.125, and we get that this error is going to be less than 1 over 8k, which k will be 4 here. It's less than 1/32nd, which is equal to 0.03125. So, from here, we know that the square root of 17 is between 4.125 and 4.09, which is quite close for something that you could honestly do fairly quickly, even in your head. Now, what gets more astounding is suppose our error, we have an error of epsilon, our guess, g, and where the square root of 2 is, or square root of n is. If we go the opposite direction and say did root n minus epsilon, if we multiply these two, this is the difference of squares, will give us n minus epsilon squared, which is less than n. Our other bound, when we'll do our next guess, g2, will be within this gap. So that means that our next error, if we call it error 2, is going to be less than a minus b squared over 8b. Now, a minus b squared, as we've shown, is going to be within n minus epsilon 1 and n plus epsilon 1. So the difference is going to be less than 2 epsilon 1 squared over 8b, which is equal to epsilon squared over 2b. Now, what's amazing about this is if our b is greater than 1, which just comes from n being greater than 1, we actually have that our error squares every time we do an iteration. For instance, if we're in n decimal places, then epsilon squared will be within 2n decimal places of the correct answer. Essentially, every time we iterate, we get twice as many digits as before, if not more, because the 8b term. Now that sounds really nice. So how do we get to our third method, which I'll call the half iteration? So, our idea for the half iteration is we had a lower bound as well. It turns out that once we subtract a minus b squared over 8b, this actually gets us really close to the right answer, even without doing an extra iteration. Now, if we use our bounds from before, a minus b squared over 8a, we can actually get even nicer bounds by going an extra step and subtracting this epsilon. Let's put this all together with the square root of 3. So, as before, we make a guess, let's say 2. We figure out what multiplies by 2 to give you 3, which is 3 halves. We take an average, which ends up being 7/4. And then this is above it, so we go another iteration, and notice that 12/7 will multiply to give you 3. And we take another average, and we end up getting 48 plus 49 is 97 over 56. Then we can do the long division. We get 1.73216. So we have an upper bound of 1.73216. Now, what is our error term? So we know that a minus b squared over 8b is bigger than, the error is bigger than a minus b squared over 8a. We had a minus b actually was 1/28. So we can put a bound on this. We get 1/28 squared over 8b, which was 12/7. And if we compute that out, we would get 1 over 8 times 12 times 4 times 28. 32 times 28 times 12 is going to be bigger than 1 over 10,000. Then on this side, we get 1 over 28 squared over 8 times our other one, which was 7/3. And so, by making this smaller, we get 1 over 28 squared times 8 times 7/3. We can just bound by 2. And we'll get 16 times 28 squared is 1 over 784 times 16. 750 times 16 will give us 12,000. So we then subtract epsilon, and we get an upper bound of 1.73216 minus 0.00008 being 1/12,000th, give us 1.73208. And so for the lower bound, we get 1.73215, and we subtract 1/10,000th, and we get 1.73205. So we get that the square root of 3 starts with 1.7320. So thanks everybody for watching. And thank you so much for your support on the previous videos. So kind, a lot of the comments that I got. It really helps me to be motivated in creating these videos, and I have some ideas for the future, which I'm excited about. I want to go through logarithms, exponentials, and even possibly touch on factorials and the gamma function. So keep up your support. Thank you so much, and see you later.